Okay, hello everyone. This is joint work with Morgan Rogers from Sorbonne, Paris Nord. And the question might seem a bit surprising if you already think you know what a monoid is. We'll come back to that. So basically, I'm going to start off like this. So I'm going to have, first of all, a programming languages introduction, and then a mathematical introduction, right? So, and in between, I'll just talk about categories and multi-categories. And then we'll get to the main story, which is 2 stages of generalization beyond what were the multi-category level, which was sort of well-known previously. Then, if we still have time, I'll just have even more layers of abstraction just for fun, and then we can finish, okay? Right, so let's start with something simple. So if we just have a language of commands, and so we use, let's say, semicolon for sequencing. So m semicolon n simply means do m followed by n. And we have a command that does nothing, skip, right? So then there's kind of 3 obvious equations that you would write down. You would say, well, sequencing is clearly going to be associative, and it has the left identity rule and the right identity rule. So you look at that, and you see clearly monoid structure, right? It is straightforward. You look at a simple sequencing, and you see monoid structure. But sometimes sequencing is more complicated than that. So in call by push value, let's look at the sequencing. So I'm not going to go a whole talk on call by push value, sorry. But the only thing that I want to sort of say or remind you is that a computation of type FA is aiming to return a value. So F is the type of return. FA is the type of returners. Okay, and this talk is not about the whole of call by push value. Just this little part, right? Just F. If you like, you can call it the core. I don't know whether it's the core, but let's call it the core for the purpose of this talk. So here we have sequencing, right? M has type FA, and N is waiting for a value of type A, and then we run them together. So M runs, it gives a value out, and N then runs, and N could have any type, computation of any type. And you have return. If V is a value, then return V as a computation. And there are 3 equations that relate sequencing and returning. And you know, when I wrote it down years ago, I gave these the obvious names. I called this one associativity, like you would, wouldn't you? I mean, what else would you call it? And I called this left identity, and I called it right identity because it seemed like the obvious name. But is this actually are these names really appropriate here? Like, what has this actually got to do with a monoid? Is it just like a vague resemblance, or is there something genuine going on here? Can we really say this is monoid structure? The last thing to sort of raise the kind of suspense level, I want to focus on the associativity law, right? The associativity law puts together 3 terms, computations, M, N, and P, right? Now, the left one is a bit different from the other 2 because N has this sequencing variable X, right? P has this sequencing variable Y, but M, the one on the left, has no sequencing variable. So we see here in the associativity law, the left term is special, no sequencing variable. Also, the right term is special, like M has F-type, N has F-type, but P can have any type. So the right term is also special. So this is what, we didn't see this in the simple language of programs, right? This is very specific to call by push value. We're seeing that when we have the associativity law, the left term is special in one way, and the right term is special in a different way. So this helps us to think, this is really getting us to think about this question. If we are going to be able to say that this is a monoid in some way, whatever that means, we somehow need to account for these 2 aspects, the left being special in one way and the right being special in another way. Okay, that's the programming languages introduction, right? Now it's category theory all the way. Right. Okay, well, before we get that, right, I'm going to give you a definition of category, right? Just to emphasize 2 points. So I'm just basically going through the definition of category and multi-category. I just want to take 2 points. So first of all, size issues are a big deal in this story. And when we deal with category theory, we always have to worry about size issues, and it's a pain. Secondly, in a category, a morphism goes from one object to one object, right? So let's quickly remember. So a category, if I want to emphasize these restrictions, I'll say a light category, right? That's got a class of objects and sets of morphism. I call these Hom sets. They don't have to be disjoint. They're just sets of morphisms. And then you have identities and compositions, and you have the three laws. So with this definition, we see that set is a category. And then sometimes in the narrative, this is where it becomes a pain, you want to talk about things where you have more than a class of objects or more than a set of morphisms, and then you start talking about arbitrary collections, and you say this is a hyperlarge category. So, for example, you've got the hyperlarge category of all categories, right? So if I just say category, I mean this kind, but if I want to be more general, I would say hyperlarge category. Okay. Multi-categories, the basic difference is that in a multi-category, morphism goes from a list of objects to an object. Not from one to one, but from a list to one. Sometimes we write it like this, from left to right. And in this paper, we mostly have diagrams going downwards. I mean, every author has a different convention where they go leftwards or downwards or whatever, but we're going downwards. So we've got a class of objects, Hom sets for every sequence and object, and then identities are unary maps, and we compose at a single port, right? You've got a morphism G going from a list, and there's one of the inputs, and we compose into it. That's how composition works in a multi-category. And then we've got a bunch of equations, and I'm just going to list them. So you've got, call it left and right identity. I mean, left and right doesn't really work here. It should be upper and lower because we're going downwards. Sorry about that. But I'm so used to saying left and right identity. We have associativity like that, sort of one into another into another. And then finally, we've got this kind of interchange law where you have two different things, and it doesn't matter which way around you do the composition, right? So that's what a multi-category is. Many of you will already be familiar with that. Some of you won't be. I should say, just again, if you're not familiar with monoidal categories, you can ignore this slide, but a lot of you will be familiar, so I need to say. So sometimes in a multi-category, you can tensor together objects. I'm not going to go into the details. And Hermida called that a representable multi-category, and he showed that such a multi-category corresponds to a monoidal category. Now, various things are possible. So you have examples of multi-categories where the tensors exist and they're straightforward, examples where they exist and they're complicated, examples where they don't exist for size reasons. That's very common in the examples that in this talk, and also examples where they don't exist for other reasons. All of those things are possible. Because of these two here, not so much because of this one, which isn't really relevant, the last one is not really relevant to this talk, but because of these two, it's more convenient to work with multi-categories rather than the more restrictive monoidal categories. Okay. So now we can start off, the introduction properly. Right, so what is a monoid? The simple answer that you're all waiting for, right? A monoid is a set, called the carrier, equipped with an associative binary operation, which we call the multiplication, and a unit. And then a homomorphism between monoids, that's a function that preserves structure. The thing is that in all kinds of situations, we encounter something that seems to, it's not a monoid, but it looks like a monoid, right? We have a carrier, we have something that looks like a multiplication and a unit, and we have three equations, and we naturally call one of those equations associativity, and the other two, we call them left identity and right identity. So we see the pattern of a monoid, even if it's not actually this. And here are some of the examples. I could expand this list, but we have rings, we have quantiles. Oh, that's a typo. That should say monad on a category A. And category on a class of you fix a class of objects and you consider category on that class of objects. So we have this notion of a monoid and a multi-category. Actually, Damian yesterday gave a version of this in a monoidal category, but we're doing it here in a multi-category. So I saw this in Latest 2002. I'm sure it's much older than that, but this was the earliest thing I could find. So in a multi-category, you can talk about You know, it's an object with a binary operation and a nullary operation satisfying the three laws. So multi-category gives you enough structure to define monoid. And again, you can define homomorphism in the same way. You cannot, by the way, describe distributive law in a multi-category. There you really do need something different, such as a monoidal category. But we're not dealing with distributive laws, just monoids. Okay, so then we get these examples, like monoid is a monoid in sets. Ring is a monoid in abelian groups. This is quite common when you learn about monoidal categories or multi-categories. You see this list of examples. Quantile is a monoid in complete sublattices. A monad on A is a monoid in endofunctors. A category on the class E is a monoid in the multi-category of set-valued endomatrices on E. This one is not representable, so we really do need, it's because E is a class and we have Hom sets. Because of that, this isn't a monoidal category, but it is a multi-category. So this one illustrates the point that we do want that generality of multi-categories. So many of you will have heard this saying, a monad is just a monoid in the category of endofunctors. What's the problem, right? It just shows how well known this idea is. Okay, that's all background. That's all the past. But unfortunately, well, I should say, sadly, when you work with multi-categories, that doesn't include all the examples of interest. So, here are 5 things that I'm aware of which are not included in multi-category. Now, I don't know how many of you are familiar with relative monads, and I definitely don't have time to go into that in this talk, so I'm really just kind of sketching this, right? So Alton, Kirchhoff, and Oosterloo defined the notion of relative monad on a functor. So instead of having a monad on a category, you have this relative monad, they call it, on a functor. And I'm calling it forwards relative monad, because there's another paper by Spivey which does something similar, but goes the other way, backwards relative monad. In fact, these two things can be subsumed into a single concept, which is relative monad on a bimodule. That subsumes the forward and the backward. I should say that the forwards relative monad was studied in a lot of detail by Archer and McDermott in the past few years. They have at least one long paper investigating this. So this one actually generalizes the previous two, so we can largely ignore the first two. Well, I don't know, because there's interesting things to say about them, but this one does subsume forwards and backwards. Then there's sequencing model of code by push value. Again, I'm not going to define this, but what I just basically mean is you take the syntax that I showed you before and you just crudely write that down into a categorical structure. You've got a class of value objects and a class of computation objects interpreting the value types and computation types. You've got a category representing the context. You've got some structure between them, and then you just literally have some sets for the values and some sets for the computations, and you just follow the rules naively. And then lastly, you've got a category on a class span. So again, that's another one that I'm not going to define. It's just a variation on the notion of category. And this one is actually a bit artificial. We introduced it for this paper just to have something relatively simple to see what's going on, because the call by push value sequencing is a bit complicated and this one is simpler. So it's just an artificial example. But this, of course, is the one that I've used to motivate this talk, the sequencing and call by push value. Okay. So I've given you 5 examples, or you could say 3 examples, of things which are excluded by the multi-category framework for what a monoid is. But we want them to be monoids, nevertheless. So the story is that we started at the multi-category framework, monoid in a multi-category. We're going to generalize this in 2 steps. First of all, we generalize it to left skew multi-category, and that will include all the relative monads. The most general kind, which is relative monad and bimodule, will be seen as monoids in this level of generality. But that's not good enough for the call by push value sequencing. So we have to go another level of generality to biskew multi-category, and this gives us the last 2 examples. That is the story. Okay, so left skew multi-category was introduced by Burke and Lack in a paper that was very enlightening to me, because before I saw this, I was really confused by this skew stuff. But anyway, this made it all clear. So in a left skew multi-category, it's like a multi-category. But so you have class of objects. Morphisms go from a list of object to an object, but there's two kinds of morphisms. You've got the loose morphisms, which are just written like basically normal morphisms in a multi-category, again from an object list to an object. And then you've got the tight morphisms. A tight morphism goes from a non-empty object list, and I'm sure you're completely unable to see that we have a double arrowhead there, which as a convention in this paper indicates a non-empty list. Okay? It's, yeah, right, sorry about that. I can't think of anything better, but anyhow. So what we try to do is that we want to highlight, if you like, that we put a bracket around the left half of the leftmost input. It's the leftmost, it's not really the leftmost input which is special, but kind of the left part of it, if that makes sense. It's just like a pictorial intuition. And just to emphasize it, we also put a red blob on the side of the triangle. Right, hopefully that's enough emphasis. So we've got this bracket covering half of the left input and also a red blob. Right. We have a loosening operation from, so any tight morphism can be turned into a loose morphism, and we use acute for that, acute symbol for that. Now, this is generalizing multi-category. So if we were to have an ordinary multi-category, then these two Hom sets, the loose Hom set and the tight Hom set, would be the same. I mean, in the case that this list is non-empty, right? And then the loosening would just be the identity. So the loosening of F would just be the same as F. On each object, we have a tight identity. Remember, we can loosen that, so we also have a loose identity. And we have three kinds of composition. It's like, just thinking pictorially, these are the only possibilities. You can put a loose, this is loose composition, where you're putting a loose thing into a loose morphism. Or if you've got a tight morphism, you can either put a tight morphism on the left or a loose morphism in the middle. So you see, everything has to line up. You don't want to have a clash between having a, like, you couldn't have a red bullet here because there's no red bullet to underneath. So it wouldn't work. And then you basically write down all the possible versions of associativity and interchange and identity. And it's just, you just write down all of them and you require those. This is all in the paper, right? So you just say all the possible laws. In particular, you want to say that everything commutes with composition, like this commutes with loosening, and this commutes with loosening, right? So we've defined left skew multi-category. Again, this was taken from Merck and Latt. They didn't actually write it out this way, but that is, in effect, what it is. Now, if you're not familiar with, I said before that you could ignore my slide on monoidal if you didn't know about monoidal categories. I suppose you could ignore this slide if you don't know about skew monoidal categories. So, but maybe you do. So left skew monoidal category, this is an older notion than left skew multi-category. Here, you don't, it's like monoidal, but you have three coherence maps which are not required to be invertible. And you've got some, I think, 4 coherence conditions. And they showed that if you have a left skew multi-category with left tensors, again, that has to be defined, I'm not going into it, that corresponds to a left skew monoidal category. So a version of Hermida's result. The main reason I mention this actually is that if I didn't show you this slide, you really might wonder from this definition why on earth it's called skew. It seems like a very strange name, right? But it's because of this connection that it's called skew. Okay, that's all I want to say about skew monoidal. Right, going back to left skew multi-category. So now you can go through and define monoid and just make everything tight wherever you can. So if you think the multiplication, you make it, you require it to be tight. But the unit is nullary. Obviously, a nullary thing has to be loose. You can't have a nullary tight map. That doesn't make sense. And then I'm not going to write down all the laws, but look at the associativity. You keep everything tight where you can. Here, on this side, you have to loosen M in order to be able to do the composition. So you just write down the obvious things, keeping everything tight as much as possible, because you can always loosen afterwards, so it's not a problem. You're not losing anything. Okay, that's left skew multi-category. So the basic idea is that you have special morphisms where the left-hand side of the leftmost input is highlighted as special. 5 minutes left, okay. You also have okay, now we finished that level. That, as I said, includes relative monads, all the different kinds of relative monads, which I've not told you what they are, sorry about that, but anyway. Bi-skew multicategory, this is the next level. This is the new thing in this work. So we have 4 kinds of morphism. Morphism can be, tight on the left or loose on the left, and it can be tight on the right or loose on the right. So all 4 things are possible if you see that in this case, A could even be empty in the loose case. But in the other 3 cases, A must be non-empty. You can see that double arrowhead, which is so visible, right? And again, you think of this bracket as being on the left half and this bracket as being on the right half. So it might be that this is length 1. So you're highlighting the left half and the right half of the same unique input. That's an important case. For the identity, for example, is tight. You have left loosening with acute and right loosening with grave, and they're required to commute. If you start off with something like this, you could go there and there, or there to there, and you get the same. And again, you work all the different kinds of composition. You can write them all out. I can't remember how many there are. It's all in the paper. And all of the millions of associativity and interchange. You just have to work out all the possibilities and impose all of those conditions. That's bi-skew multicategory. Okay, and now we want to define monoid and homomorphism in a bi-skew multicategory. So what do? We make everything tight if possible. So the multiplication is tight, right? The unit is nullary, therefore it's loose, loose. The associativity, again, you see you've got some left loosening here and some right loosening here, but you keep everything tight as far as possible. And now try and go back. Remember what I said about the associativity and called by push value. Remember I said the left is special in one way. That's this red dot or left bracket thing, right? The right is special in a different way. That's this right bracket or red dot. Maybe we should use a different color for the right. I don't know. Maybe that would have been sensible. Okay, so the left is special, the right is special, and you see it. So I'm not, okay, so now the extra bits of abstraction. Am I running in, just to say briefly, we've got a coherence theorem. No. Okay, we've got a coherence theorem. It's like this. You define an unbiased monoid to be in a bi-skew multicategory C. An unbiased monoid is simply a map from 1 to C. What does that mean? It means instead of just having nullary and binary multiplication, you've got multiplication of all arities and all possibilities of tight and loose, and everything, all the compositions of multiplications give you multiplications. And you then show that every monoid uniquely extends to an unbiased monoid. This fact for multicategories is well known, so we're showing the same thing works for bi-skew multicategories, and so that's, if you like, it's reassuring. It tells you we're not missing anything in our definition of monoid. That's one thing I wanted to tell you. Also, I said that Burke and Latt define left-skew multicategory, and we've got this new concept of bi-skew. Well, it's not quite, you could see it a little bit differently. They actually had a higher level of abstraction of T multicategory, where T is a certain kind of operad, and then they define left-skew multicategory to be an R multicategory for a specific R. Right-skew multicategory is exactly the same. You just turn R, you'd have the same operad, but you reverse left and right. And so all we're doing is multiplying these two operads. So actually, all the ingredients that we use to build bi-skew multicategory are already there. This was really amazing to me. You start with call by push value sequencing, and you end up with this just multiplication of operads that just gives you, then apply it to their notion of multicategory, and you get bi-skew multicategory. So it was all kind of there. They don't talk about monoids, but bi-skew multicategories are kind of implicit in what they did. Okay, so those are some little extra abstract treats. Let's conclude. So now, every monoid-like notion that we've come up with, I'm aware of, that Morgan and I are aware of, is actually a monoid. So now we have a new saying that call by push value sequencing is just a monoid in the particular bi-skew multicategory that we define in great detail in section 5.4. What's the problem?
Can you compute something like 3 monoids in a multi-category, bi-skew multi-category?
Well, the free monoid honestly, I have no idea. I hadn't thought about that question. I mean, they don't always exist even in a multi-category, right? I mean, you can define a notion, which sometimes will exist. I don't know, I'd have to think about that. Sorry, I'm like... Yeah, good question. Thank you.
Is there an intuitive reason why both these forwards and backwards relative monads were both part of this left skew multi-category instead of needing sort of these left and right skew things?
Okay. No, I mean, I wouldn't say they were left and right. I called them forward and backwards. So you got functor from C to D in the one case and a functor from D to C in the other, and each of those gives you a bimodule from C to D. But they've very much got one direction in terms that you take objects in C to objects in D in both cases. So they're really going the same way.
So you only need the bi-skew thing where you have both things going on at the same time.
Yeah. So the point. So what was distinctive in the call by push value sequencing is that there's something special on the left and something special on the right. You don't get that with relative monads. It's only really special on the left, but on the right, there's nothing special going on.
Okay, thank you.
What is a group?
Oh, gosh. I thought, I mean, okay, come on, you could at least have said what is a commutative monoid. Even that would have been too hard. I don't know what a group is, sorry. None of these things seem to have commutative variants, actually. So at least these one right here, so group, no, sorry. I don't think.
So, nice talk. Thank you very much. Have you learned anything about call by push value from these investigations?
Actually, I learned a lot, but not really from the bi-skew stuff. Learning about the multi-categories, particularly about exponentiability in multi-categories, which does apply to some extent in the skew case, but this was new to me, and it led me to understand the connection between like locally indexed models of call by push value and graded models in ways that I didn't before. So I learned a lot, but it was completely sort of by the way, and it's not stuff which is sort of in the talk. See what I mean? So that's probably not very helpful. But the process of like learning and writing about this multi-categorical story actually was very educational. Yes.
So yeah, I just want to mention something that here the multiplication you described would be defined as composition. Would be described usually as composition of morphisms. Yes. So, like you have different programs or maps,
yeah,
and you compose them. So multiplication is composition of programs. Yes, you would agree with that?
Well, I mean, you could call it composition, but...
I mean, traditionally.
Yeah.
Yes. So what I mean is that, in fact, the question you ask is, what are the different kinds of categories?
Yeah.
Yes. What are the different kinds of categories that we could use? So we could imagine skew notions of categories, where we have special left maps and right maps. And I think this is the kind of universal question we're exploring, how to go beyond. And people have done that in infinity categories. So they work with simplices, simplicial sets, and as generalizations of categories. So do you have any view on that? Like, for instance, here, today we spoke about like diploids and non-associative categories. So, you know, some general notion of category, more general, non-associative maybe, or whatever, with left maps, right maps, that would organize this.
Okay, I didn't think of this as a generalization of category, because I thought it was a generalization of multi-category, where we still have all the, as I said, when we define bi-skew multi-category, we have all the associativity and interchange and identity laws. And what's changing is that we have more kinds of HOM set. But maybe there is a connection there to what you're saying. I think that could be.
I think it's time to thank the speaker.